So, let's take a look at the question today, and then we'll jump into our notes. And we've got a very important round of notes today. So let's take a look. Your friend goes to the moon. He finds a 10 Newton gold bar there. That makes him super excited. You also find a 10 Newton gold bar at the local beach. Maybe Bradford Beach or Grant Park Beach. So who do you suppose is richer in this case? Why is that?
Because takes stuff away from around the moon, right?
Other way around, actually. Things are a bit lighter on the moon.
Oh, okay then.
You're right, though.
Oh.
Because if things are lighter on the moon, what do you suppose happens if you bring them back to Earth? Yeah. So your friend who has a gold bar that seems to him to be like 10 newtons, but I don't know, maybe just say it's like 20 pounds. It feels like it's 20 pounds to him. When he brings it back to Earth, it's going to weigh a lot more and therefore be worth a lot more. So your friend is richer in this case. Alrighty. Like I said, we've got a big, important round of notes today. And you can title your notes, Vectors on an Incline. Vectors on an Incline. I've got 4 examples I'd like to power through here. And they include probably the most difficult examples to work through pretty much in all of physics here. These force diagrams I know can look a little complicated. We've seen that already. And this is going to be about as complicated as they're going to get today. So if you're even along for the ride a little bit in this lesson, you're in good shape, because we will be going through and practicing this a lot over the coming days and weeks. So if you get lost a little bit, that's all right, but please make sure you ask questions as they come up, because chances are a lot of other people have those same questions as we go through this. So, who is ready to dive into the 4 big examples today? All right, Amari, I knew I could count on you. Okay.
I have a question, Jake.
Yes.
You said name it vectors. What?
Vectors on an incline. Here's our first example. And with this example, just like every example we've done so far in this chapter, there is a 2-step process that we have to follow to solve all these problems. Step 1, create a force diagram. And step 2, create a force equation. So we're going to follow those same steps here. What's one force acting on this box that's attached to a string? Gravity and tension, absolutely. Gravity's going down. Tension is going up. There is no normal force here because it's not on the ground. So we've just got this string holding it up, and that's it. So tension force up, gravity down. Therefore, if I want to make a force equation, all I do is I take all the forces going up minus all the forces going down. Once you do that, you're finished with that equation. That's all she wrote. Typically, for a problem like this, you'll be asked to solve for the tension force. You'd probably be given enough information to find force of gravity. Like if it says it's maybe 10 kilograms, how would you find force of gravity? Exactly. Force of gravity is mass times g, which in this case is 10 times 9.8. 10 for the mass, 9.8 is the gravitational acceleration on Earth. So you'd have 98 newtons. But yeah, force diagram, force equation, that's how you do this. All right, we're a quarter of the way through. Example number 2. We add a string. We've got to see how this changes for us. So if I've got two strings now, and I want to create my force diagram, I'm going to make my dot a little bit bigger so I can have two forces going up. Gravity's still going down, no question about that. But going up, we've got two separate tension forces now instead of one. And so that's what we'd have. So if I wanted to, if I wanted to make this into a force equation then, all I'm going to do is add up all the forces going up, and I'm going to subtract all the forces going down. Questions on why that happens? Everybody still aboard the train? Good. All right. So those were kind of our warm-up questions. Now we get to the main event. There's only two more examples I want to get through before the end of the hour. They're going to take a little bit of time. Try not to let them intimidate you when you see them. So there's our setup. We've got our block. It's attached to two strings. One string is pulling it to the left. One string is pulling it up and to the right. And so the question is, how do we deal with this? Well, we deal with this the same way we deal with every other force problem that we have in this chapter. One, we have to make a force diagram. And two, we got to make a force equation. So if I want to make a force diagram out of this, I start with my dot, and all I do is, again, you put forces in here that are acting as a push or a pull to this block. So obviously gravity is pulling it down, so gravity's going down. And we can see the two strings. It's partially being pulled up like this, partially being pulled across like that, and so those are two other forces that we have to insert here. Tension force 1 is yanking it that way. And tension force 2 goes that way. So that's our force diagram there. Now, we might want to put this 50-degree angle in here too. So there's your 50-degree angle. Now, if that angle's 50 degrees, can anybody tell me what this one's going to be? 50, exactly. Because of math, right? If you know this angle, we know this one. That's some math law there. If you are unsure as to whether or not these two are equal, the best thing you can do is just ask yourself, what happens if this angle gets smaller? If this angle gets smaller, this one gets smaller too. And that's a pretty good sign that they're both going to be the same thing. So once we get that 50-degree angle in there, we can take that away. So there's our force diagram. And typically, this kind of a question is going to ask us for, two things. If we know tension force 1, it's probably going to ask us what tension force 2 is equal to and what the force of gravity is equal to. And that's something that we can actually find if all we know is tension force 1. Tension force 1 is 42 newtons. We're going to see if we can use that to solve for the other two things. So one force here is not acting exactly in the x or y direction. That's Ft2. It's partially acting to the right. It's partially acting up. So we got to make sure that we take that into account. The portion of this force that's acting to the right, I would call Ft2x. It's kind of a long name because it's tension force 2, and it's the portion of that that's pulling to the right. And of course, there's part of that force that's acting upward. So that's Ft2y. And once you have this all drawn in, we go ahead and we solve this the exact same way we've solved every other force diagram so far in this chapter. We look at the x and y directions, and hopefully from those directions, we can figure out what these forces are going to be equal to. So in the x direction, we've got two things. We've got tension 2 to the right and tension 1 to the left. So, before I go on, any questions about the force diagram? Okay. So in the x direction, we've got Ft2x going to the right. And that's being opposed by Ft1. That's going to the left. So I have to subtract those two. And you can kind of see where this is headed. If I want to solve for Ft2x, all I got to do is put Ft1 on the other side. You can see that they're both going to be the same number. And of course, Ft1 is given to us, 42 newtons right there. And this helps us in a huge, huge way. Because if we look at our force diagram, I'm looking for this force up here and this one down here. But I don't know any of the information in this triangle here, except that it's 50 degrees. Well, if Ft2x is equal to the same thing as Ft1, that means this side of the triangle is 42. And if I know that this side of the triangle is 42, I can use that to solve for the hypotenuse. Questions on that reasoning? So if I know my adjacent side is 42, and I know my angle is 50 degrees, I can use a cosine equation to figure out what the hypotenuse is going to be. And you use cosine because cosine is equal to adjacent over hypotenuse, and those are the two pieces of information that we're looking at right here. So cosine of 50 is equal to adjacent over hypotenuse Ft2. That's what we're looking for. And we can use that equation to solve for Ft2. Now this looks a little bit different.
For what?
Go ahead, yes.
For y,
Well, we're solving for the red one here. We haven't done anything in the y direction yet. Because we used a horizontal force equation to figure out that this is 42, and now we're just going to use that fact that this side of the triangle is 42 in order to solve for the hypotenuse. So if I carry this equation the rest of the way through then, this is going to look a little bit different from what we've done in the past, because usually we're solving for the numerator. Here we're solving for the denominator. So what ends up happening is we got to multiply both sides by ft2 and then divide both sides by cosine 50, and we have an equation that looks a little different from what we're used to. So ft2 is going to be over here on the left, and once that's over on the left, we divide both sides by cosine 50. So we have 42 over the cosine of 50. And if you plug that into your calculator, and your calculator is properly in degree mode, you should end up with 65.3 newtons. And that would be one of the answers that we're looking for here. That would be equal to our hypotenuse. Questions so far? I know this is a lot. Okay. Again, as you have questions, please let me know. So that's as far as we can go in the x direction. Now, if we want to solve for force of gravity, we got to look at what's going on in the y direction. Because after all, force of gravity is a vertical force. So we need to start looking at some vertical forces to see what the deal is with that. So vertically in the y direction, I've got two forces. I've got tension 2 in the y direction going up, and I've got gravity going down. And so that's what my force equation is going to be. And you can see where this is going. It's kind of the same thing as before. Now, if I want to find my force of gravity, all I got to do is move it to the other side, and you can see it's going to be equal to tension 2 in the y direction. So once we get to this point, now our goal is to figure out tension 2 in the y direction, because once we have that, we have our answer for force of gravity. So tension 2 in the y direction is over there, and we've got a couple different ways we can solve this now. Remember, we found the hypotenuse to be 65.3, so we've got two sides of the triangle. And we can solve for that third side. We could either use a sine function, or we could use a tangent function. I'm going to use sine just because I'm kind of used to going back and forth with sine and cosine. So if I want to use sine, it would be the sine of 50 is equal to opposite, which is ft2y, over the hypotenuse, 65.3. And I can use this equation to solve for ft2y then. And you do that by multiplying both sides by 65.3. And if you do the math right on this one, you should get an even 50. So in this case, 50 newtons is equal to tension 2 in the y direction. And as you can see from our force equation up here, tension 2 in the y direction is equal to force of gravity. So 50 newtons is equal to that too. So there we go. Take a deep breath. I remember when I did that helium thing? That was fun. So that deep breath reminded me of. Yeah, things were much easier back then. Back in the glory days when it was warm out. Final questions on this madness here. Okay. We'll be doing more practice with that as the days and weeks go on. But we've got one more example to get through now. And if that one didn't blow your minds, chances are this one's going to. Now, as we're going through this, and as it looks complicated, you need to know that the example that we're going to tackle right now is probably the single hardest physics example that you're going to see in this class. So I say that because that means if you don't follow it, that's okay, because we're going to be going through this and practicing this a lot. But if you are able to hang on for this ride, you're in really good shape if you hang on all the way to the end. So let's see what we can do here, and if you have questions as we go through, please let me know, because this is a really important example. So, everybody ready?
Set.
Go! Here we go! So far we've been dealing with objects that are on a flat surface. Not anymore. So that's what we know, and that's our starting point. So we've got ourselves a little box that's attached to a string. The string is holding it in place, keeping it from falling down, sliding down. And it's sitting on this 20-degree incline. So, typically for these kinds of problems, you'll be asked to solve for a tension force and a normal force. And again, just like the other examples, if you're asked for those, you don't look in your force equation sheet for them. You realize that in this section, in order to solve any of these problems, we got to do a force diagram, and then we got to do a force equation. From that force equation, we should be able to figure these things out. So, what are some forces acting on our box? Gravity! Gravity is acting straight down, as always. We haven't done anything wrong yet in this, the hardest example that we've dealt with. Yes? You might want to for this one, just because we're going to be doing something a little bit different. We are going to make a separate force diagram after we're done with this, but yeah. So gravity is going down. There's also a normal force because we're on a table of some sort, and that normal force is always going to act perpendicular to our surface. So it's going straight up. That's our normal force. In addition, we've got this string here, and that's holding our box in place. So that would be a tension force. And those are our three forces. And this is where we might start to cry just a little bit. Because, so far, when we've been dealing with these examples, there's only been one force that has not been acting exactly vertically or exactly horizontally. Now we got two. And that's going to make our lives doubly as difficult. However, there is a way that we can make this a little bit easier on ourselves. And that's what you're going to learn right now. And this is going to seem kind of strange, but in reality, it does make this problem easier for us to deal with. You guys know about the X and Y axes, right?
Yeah.
X is usually horizontal, Y is vertical. Typically, that's how they go. But for this example, it's actually easier for us if we take those two axes and we just rotate them slightly in such a way that the normal force lines up with one and the tension force lines up with one. Because then the only force that isn't lined up with one of those two axes is gravity. And that's the only one we gotta, go through those weirdo angles with in order to solve. So that's what we're gonna do. We're gonna take our y-axis and we're gonna rotate it a little bit clockwise, and that y-axis is going to be in line with the normal force. And our x-axis is rotated a little bit the same way. It's going to be in line with the tension force. So those are our new axes. X-axis will always run parallel to your surface. Y-axis will always run perpendicular to your surface. Questions so far on this? Yes?
I don't get it because this is X is already this way and Y is this way.
Yeah, X is usually horizontal and Y is vertical. But we can do whatever we want with those axes as long as we keep them so that they're perpendicular to each other. As long as these are 90-degree angles between them, we can rotate them or spin them however we want. And that's what we're doing here. We're taking that X and Y axis that's usually up, down, left, right, and we're just turning it a little bit clockwise so that both axes match up with two forces instead of just one. Yep. Questions so far here? Okay, so now we're going to reproduce this over here and make it look a little bit nicer. So gravity is down. Normal force is up and to the right a little bit. Of course, tension force is going to be up and to the left. Now, of course, things don't stay this easy for long. We got to put in those new axes. So this is our new y-axis. That's our new x-axis. And because x lines up with tension force and y lines up with normal force, it's going to make our lives way easier when we have to deal with some of these angles. And speaking of those angles, it's probably best we put some of those in right now. So here's how you figure out what all these little angles are going to be. Step one, you want to just draw a little dotted line. Cute little dotted line like that. And see if you can follow the reasoning here. This 20-degree angle is either going to be on the left side or the right side. Now you can kind of tell this is a small angle, and just by looking at it, you can see it's going to fit in here better. But if you're ever in doubt of that, one thing you can do is just say, if you take this triangle and you're not allowed to spin it or rotate it, just ask yourself what side that wedge would slide into. If I just shift it up and move it to the right, it slides right in there. It would not slide in here because this is the wrong side. The wedge is right on the right side, so it's only going to slide in that position. So 20 degrees is going to go right here. Any guesses on what's going to go there?
20 degrees.
Good guess. Nope.
70.
70, yep.
Oh.
They have to add up to 90.
90.
And you just alternate as you go around. So there we go. So the questions on any of the angles or anything? As we continue then, now we're a little bit happier than we were. We've dried our tears, and we're excited a little bit now even, because tension is in the x direction. So we don't have to deal with any weird angles there. Normal force is in the y direction. We don't have to deal with any strange angles there either. But we do have to deal with force of gravity, because now it's going in both the y direction and the x direction. So we have to make sure that we're aware of that and taking that into account. Here's how we do that. You don't have to follow this exactly, but if you want to make your arrows for force of gravity in the x direction and force of gravity in the y direction just the right length, what you would do is you'd start from the tip of your arrow here, and you just make a little dotted line that reaches your x-axis and hits it at a right angle. And you'd do the same for the y-axis. You'd make a little dotted line that encounters it at a right angle, and that's how you would draw your arrow for the x direction and the y direction. Again, you don't have to follow that procedure. The main thing is that you realize that this force of gravity here, this green line, the force of gravity coming down, this is always your hypotenuse. This is always the longest of these three forces that we just drew in. You have to make sure that you realize that. So in the x direction, of course, this is going to be force of gravity in the x direction, and this will be force of gravity in the y direction. And that's really where the physics ends, and this turns into a math problem. Questions on this, any parts of this picture? Okay, so in order to finish this, like I mentioned, typically this type of a problem will ask you to solve for tension force and normal force. So if we want to solve for tension force, we got to look in the x direction. So let's make a force equation in the x direction. Pulling up, we've got tension force. Pulling down, we've got gravity in the x direction. They're going opposite directions, that's why they're subtracted. It's equal to 0. Do you see how we're going to find tension force?
Yes.
Yeah! Tension force is going to be equal to force of gravity in the x direction. And so now our job is to solve for FGX here. Now, in order to do that, we need whatever this green line is. And we can figure that out. How do we solve for force of gravity? Anybody remember the equation?
Mass times 9.8.
Yep, mass times 9.8. It says the mass is 40. And if we do that math, we're going to get 392 newtons. So that 392 goes right here. It's the green line. Maybe I'll make it green just to make sure that we're clear on that. And that's going to be the hypotenuse of our triangle there. So, if I'm looking for FGX, that is the adjacent side of the 70-degree angle. So if I'm dealing with an adjacent side and I have the hypotenuse, that automatically means I have to use a cosine function. So the cosine of 70 degrees is equal to adjacent, which is FGX, over hypotenuse, which is 392. And I can use that to solve for FGX, just like we've done in the past. Multiply both sides by 392. And you're home free. And if you multiply that all out, I think you should end up with 134 newtons. And because 134 newtons is equal to FGX, that's also equal to tension force. Boy, does this look complicated or what?
Yes.
You take a picture of this with your phone and show your parents, and they will be super impressed.
I'm gonna take a picture of it and show them.
Go for it, yeah. We do have one more thing that we want to get through here. So actually, yeah, go ahead.
I'm like, I know how to do that. Hey, Danielle, just scoot your head down just a little bit. Oh my gosh. Thanks.
All right. So now we got to solve for the other thing. We got to solve for the normal force. And this is done in the exact same way. So if we're looking at the y direction now, we've got normal force up, force of gravity in the y direction down. So we subtract the two, and we set it equal to 0. So if I want to solve for normal force, it's just going to be equal to FGY. Whoops. There we go. So yeah. So if I want to solve for FGY, you can actually do this in one of two ways. If you're the type of person that's like, I just want to deal with this one triangle, then you could use this part of the triangle, and that part of the triangle is going to be equal to FGY. If you're like me, and you'd rather just stick with the arrows and the directions that they're going, I would solve using this triangle. So if I'm doing that, it's the adjacent side of this 20-degree angle. So I would use cosine again. Cosine of 20 is equal to adjacent, which is FGY, over hypotenuse, which is 392. And you get your answer the same way that we did in the previous example, except we've got a different angle here. 20 degrees instead of 70. And it looks like that comes out to 368 newtons. So then 368 newtons is equal to FGY. And what that means then is that it's also equal to your normal force. Now, like what I was saying before, if you want to just stick with this triangle, you could solve for this side, and you'd be solving for the same thing, except your equation would be sine of 70 equals FGY over 392, because it would be the opposite side. But you'll get the exact same answer. So this would read 392 sine 70. So it's a personal preference, whatever you feel like. Personally, I like doing it the way I did it the first time there, staying in line with the arrows. Final questions on any of this? I know this is hard, and I feel for you. I remember seeing it for the first time myself and being intimidated. But we will be practicing this more in the coming days and weeks, and you'll get more comfortable with it. I do have a piece of homework for you that will be due on Friday. You'll have class time tomorrow to work on it. So make sure, as I hand it to you,